Morning, everyone. Questions while we wait? Morning, everyone. Come on in. Questions? Anybody? No, we're good. Material? Material is good. I'm not sure what's on the midterm yet. It's still far enough away. Certainly everything we did so far. To answer Jordan's question, there is no difference. No word yet on epsilon delta, but I mean, I plan to figure everything out over the weekend. So next week we'll have a definitive answer as to what's going on. Maxwell was correct. 1 over negative infinity is the same as 1 over infinity, right? I mean, think of infinity is a very large number, right? So 1 over a very large number, these fractions keep getting smaller and smaller, closer and closer to 0. Same with the negative. If you factor out the negative, you still have a 1 over infinity. Aiden, let's wait until next week. If we decide to put epsilon delta on the exam, we'll discuss it again in class. Well, I'm looking at Jordan's question here. How does evaluating limits at positive versus negative infinity produce a different answer? You know the limit is the behavior of the function. So limit as x goes to infinity is the behavior of the function for large values of x. Limit as x goes to negative infinity is the behavior of the function for large negative values of x. So you understand that whatever happens here has absolutely no effect on what happens here. If you give me any two numbers or any kind of infinity, I can draw a function whose limit on one side is one number and limit on the other side is another number, right? Negative 1 and 3 here we go. Limit as x goes to infinity is 3. Limit as x goes to Negative infinity is -1. Whatever happens on one side has absolutely no effect on the other. Let's look at Lita's question here. Limit as x goes to 0 of sine 5x over 3x. You know what to do, right? Again, I cannot stress this enough. There is no way for you to get the 5 out of the sine. What we did see was the limit as h goes to 0 of sine h over h. We saw that to be 1. And that's what we're going to use here. We're going to transform this 3x into a 5x. And then if you want, you can make a change of variables. And how do we change the 3 into a 5? Well, you multiply by 1, namely 5 over 5. You multiply by 1, you're not changing anything. And you can rewrite this as 5 sine of 5x over 3 times 5x. And now, this is just a constant, so you can take that out. And now, if you want, although you don't have to, but if you want to convince yourself, you can make a change of variables. Let h equals 5x. As x goes to 0, h also goes to 0. So this is really the same as the limit as h goes to 0 of sine h over h. And that limit is 1. So the whole thing goes to 5 over 3. Very nice. How are we doing here? Questions? Let's go back to the question I gave you. People are asking about web work. I'll open up a web work if that's where we're at. I mean, I'll have a look. I'll have a look after class. And if we've done enough of the material, we'll open it up. I had left you with the following question. What is the derivative of sine of x squared? And this sine of x squared here can be viewed as the composition of two functions. If we define f of x as sine x and g of x as x squared, then sine of x squared is really the composition of f and g, right? G is x squared, and everywhere you see an x in your function, you replace with x squared, and you get sine of x squared, right? So this function here, sine of x squared, is really the composition of two functions. So if we're asking what is the derivative of this, we're really asking, in general, what is the derivative of a composition of functions? And this is answered via the following theorem. known as the chain rule. If you start with two differentiable functions, let f and g be differentiable, then the composition is differentiable. And the derivative so the derivative of a composition, derivative of f of g, differentiate the outer function first times the derivative of the inside. While we're here, let me give you a reformulation of this, an important reformulation. If you let u be g of x, then and y be f of g of x, what is this chain rule telling us? This is the derivative of y with respect to x. So dy dx, this is f prime of u. Right? So dy dx is f prime of u times g prime, but this f prime of u, right, this is f of u, so this is really dy du, and this g prime is really du dx, which can be remembered by thinking of crossing out these du's in a terrible abuse of notation, but this is a way for you to remember. dy dx, dy du, du dx, the du's cancel, and you're left with the dy dx again. Right, so that's the important thing to remember. Dy dx is dy du, du dx. A second reformulation of the chain rule. Questions here? Let's see a few examples. Consider this. Let's take a moment and rewrite this function as the composition of two simpler functions whose derivative we're already comfortable with. Right? This can be viewed as the composition of what two functions? You tell me. X to the 50 and this one, this polynomial of degree 5. Very nice. Right? So in other words, f of x is really the composition g of h of x. Is that clear, everyone? Is everybody comfortable with that? Right? This thing, this is g of h, this is your h. And everywhere you see an x and g, you replace with this. So you get that to the 50. Absolutely. So what is the derivative? Right? Chain rule. Let me erase it, but I'll rewrite it up there so we don't forget it. The chain rule tells us that the derivative of the composition f prime of g, g prime of x. Right? Differentiate the outer function first, and then multiply by the derivative of the inside. So here we're looking at g of h of x. So here, the derivative of f, right? I mean, it's a composition of g and h here, so it's g prime of h times h prime of x, right? Here the g plays the role of f, whereas h plays the role of g. I mean, I'm sure you're not confused by that here. What is g prime? Right? You've broken up f into a composition of simpler functions, both of whose derivatives you're very comfortable with. Derivative of g prime, you know what it is. It's 50 x to the 49. H prime, derivative of this, 5x to the 4 plus 6x minus 1. So this g prime of h, right? So everywhere you see an x and g prime, we'll replace with this. What do we get? 50 x to the 5 plus 3x squared minus x to the 49 times h prime, the derivative of the inside. There it is. Somebody's asking, how do we get those combinations? Inspection, just by looking. Just by looking. I mean, you know, in the beginning of the course, we did a lot of composition here. Composition of functions, right? We considered that. So, I mean, in this case, it's pretty clear that it's a composition of those two functions. Let me point out that there isn't a unique answer to this, right? I mean, you can usually decompose a function as the composition of two functions in more than one way. It doesn't matter. The answers will coincide. Michael is asking how the chain rule is derived. Well, let me suggest that if you start with this assumption, you can actually prove it using the limit definition. I'll invite you to try that out, see if you can come up with the answer. And yeah, I mean, how, so that's assuming that you know this to begin with. How would you have come up with that? Maybe by looking at easy examples, right? I mean, if you had something like 2 to the x to the 50, and you worked out this derivative, the usual way, what do I mean by usual way? This is really 2 to the 50 times x to the 50. So you know what the answer is going to be. But if you try to differentiate this, maybe it would lead you to that idea. It's because I've already used the f here. I don't want to, yeah. Let's try another one. Consider this. Let's do the same exercise. Let us decompose this as the composition of two simpler functions. Two functions whose derivative you're already familiar with. Right? Perhaps you might want to rewrite this as x squared minus 1 to the, what exponent? You know what exponent. To the negative 1/3, thank you. Right, and now it's pretty clear. Right, now it's clear that this is the composition of functions g and h. What functions? Right? X to the minus 1/3 and x squared minus 1. Absolutely, thank you. Right? Both of which you know the derivatives of. Right? You know that the derivative of g is minus 1/3 x to the minus 4/3. And you know the derivative of h is just 2x. And now, by the chain rule, the derivative of f, well, f of x, which is the composition of g and h. I mean, does everybody see that when you compose these two, when you replace x with this, you get exactly what we're looking for, right? So f is the composition of g and h. So the derivative of f is, according to the chain rule, differentiate the outer function leaving the inner function fixed, times the derivative of the inside. So here, g prime is this, and everywhere you see an x in g prime, you replace with h. Right? I mean, do I want to take an extra step here and say g prime of x squared minus 1? H prime, we just saw was 2x. And here, everywhere you see an x in g prime, you replace with x squared minus 1. So minus 1/3 x squared minus 1 to the negative 4/3 times the 2x. Let's go back to the previous example. We can just leave it as is for now. The important thing is that we practice the chain rule. Eventually, of course, you'll be asked to simplify, but for right now, we can leave it as is. In this example, the function was x to the 5 plus 3x squared minus x to the 50. Right? What I want to bring your attention to, I mean, we'll do one more example of this decomposition, but I mean, eventually, this is too time consuming, and you have to be able to see it without explicitly writing the functions you're composing. What I want to bring your attention to is how we're going to achieve that. What you have to recognize is that your function is something to the power 50, like an x to the 50. So you would differentiate the power, right? So 50, blah, blah, blah to the 49, and then you differentiate the inside. That's what the chain rule says. Here, you have something to the negative 1/3. So you differentiate the power, negative 1/3, blah, 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 to the negative 4/3, and then you differentiate the inside. Right? You differentiate the outer function, leaving the inside fixed, and then you differentiate the inside. That's what the chain rule says. Let's do another one. Don't let the t fool you here, whether it's t or x or any other. Exactly that, as Jennifer points out, a very nice observation. You're actually always using the chain rule. Always. Right? If you're differentiating something like cosine x, the derivative of cosine x, well, derivative of cosine is negative sine, and then you differentiate the inside. But the derivative of x is just 1. So there it is, but yeah. Right? For the last time, let's decompose this as the composition of two functions. Right? This is the composition of f and g. What f, what g? You tell me. F is t to the 4. G is 1 over 2t plus 1. Absolutely. And you know the derivative of f. 4t cubed. You know the derivative of g. Well, I mean, it's maybe not immediately clear, but we can differentiate this using the quotient rule, because it is a quotient. Let's do it. Vu prime minus uv prime all over v squared. So what is that? That's gone. Minus 2 over 2t plus 1 squared. You could decide to rewrite this as 2t plus 1 to the minus 4. In that case, your two functions would be different. So that goes back to what I was suggesting earlier, namely that the decomposition as a composition of functions need not be unique, right? Here you're going to have immediately two different answers, and that's fine. The derivatives you get, though, two different ways will be the same. And as Matt is suggesting, you could have differentiated this viewed in this way, which itself is a composition of two simpler functions. Very nice. Very nice. We applied the quotient rule, but you could view this as the composition of two simpler functions, namely t to the negative 1 and 2t plus 1. Why don't we do that quickly and see what is happening, and see that it's going to give us this as the answer. The derivative of j is negative t to the negative 2. Negative t to the negative 2. And the derivative of k is, of course, just 2. So the derivative of this, the derivative of 2t minus plus 1 to the negative 1, right, is j prime of k. So minus 2t plus 1 to the minus 2 times k prime. Exactly the answer we had. Yep, so there it is. And let's finish that up, right? Because we still don't have the derivative of h yet, and that was the question we were looking for. So put everything together. H prime of t, which was f prime of g of t times g prime of t. So f prime of g is this, 1 over 2t plus 1. G prime we worked out to be minus 2 over 2t plus 1 squared. And f prime of this, everywhere you see a t in f prime, you replace with that. So we have 4, 1 over 2t plus 1 cubed times this. Susan is asking if on an exam we have to decompose the functions. As I have suggested, this is the last time I'm actually going to do that. But on an exam, the question could ask you to decompose, right? That would be a nice link between the pre-calculus stuff and the stuff we're doing now. We suggested that earlier, Maxwell, right? You could also rewrite it this way, and then you'd have two different functions. Absolutely. And what I want to bring your attention to is the fact that, again, right, this is the last time I'm actually decomposing, unless somebody wants me to do it. But what we're going to do is we're going to be looking at our function, right? Let's write it out here. H of t is this, and we're going to ask, what are we looking at? What is the derivative? We're looking for the derivative. And what is this? Well, this is something to the power 4. So we're going to differentiate the power 4, right? The t to the 4. So we get a 4, blah, 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 cubed. And then you differentiate the inside. Here I'm going to leave it as this, because it's not immediately clear what the derivative of that is. You know, you'd have to apply the quotient rule, but I mean, we did that separately and we got that. This is how we're going to do it from now on. Case in point. Cosine squared. Can you write out the chain rule formula? It's right here. The one without separating the functions. Did you mean dy dx is dy du dx? On an exam, you're going to want to show all your work. You could have treated this as 2t plus 1 to the negative 1 and applied the chain rule again. Thank you. Cosine squared of theta, of course. Yeah. So we're asking the question, what is the derivative? And what are you looking at? You have something squared. Part marks will be given, absolutely, if you show your work. We have something squared. What is the derivative? Well, you differentiate the square first, right? Like an x squared, if you will. And you get 2 times this to the power 1. And then you differentiate the inside. Inside is a cos. The derivative of cos, negative sine. In other words, minus 2 sine cos. As Jacob suggests, hypothetically, you could, you mean in this case, you could treat this as cosine theta times cosine theta? Sure. So you could apply the product rule, absolutely. And then, as Nandini suggests, you would get a trig identity. What page? 206. So here, I mean, of course, you could treat it as a product and everything is nice. What if we had something less manageable? What if the square was on the theta? Yeah. We'll answer that afterwards. What if you had a tangent to the power 10? Then you probably don't want to use a product, right? You probably don't want to say tangent times tangent times tangent 10 times. Although you could. You have options. Instead, what? You've got power 10 here, and we're going to we have something to the 10. We're going to differentiate that power. 10 times the something to the power 9. And then you differentiate the inside. Inside is tangent. Derivative of tangent is? You know what it is. We saw it last time. I'm sure you've committed it to memory already. Secant squared. Consider sine of x squared. Sine of x squared, which really was the question I left you with last time, right? It's the question which motivated this chain rule. What is the derivative of sine of x squared? Well, what do you have here? You have sine of something. The derivative of sine is? Derivative of sine is cosine. And then you differentiate the inside. Derivative of x squared is 2x. There it is. How are we doing here? Is there a rule for that? Rule for what? Maxwell is asking if there's a rule for why do we do 2 sine x? Where are we? I don't see a 2 sine x anywhere. I mean, there are many questions that I don't understand. We're applying the chain rule here, right? Chain rule, people? Right? Do we want to decompose this as the composition of 2 functions? This is the composition of sine x and x squared, right? The derivative here is cos x, and the derivative here is 2x, and this is viewed as g of h of x, right? H of x is x squared. Everywhere you see an x in your function g, replaced with x squared, you've got sine of x squared. Now we saw, when we treated it as a definition, we saw the derivative of e to the x is e to the x. Question arises naturally, what about other exponential functions? What is the derivative of a to the x? Well, we're now in a position to answer that. You know that exponentials and logarithms are inverse functions of each other. So a to the x is the same thing as e to the ln a to the x. Right? Exponentials and logarithms are inverse functions of each other, so these just cancel out, and you're left with a to the x. So instead of differentiating this, I can differentiate that. Well, this, by properties of logarithm, I can bring the x down here. So this is e to the x ln a. So the derivative of a to the x is going to be the derivative of e to the x ln a. But the derivative of this, it's e to the something. So the derivative is e to that something times the derivative of the inside. But this is x times a constant. So the derivative is just ln a. But e to the x ln a is a to the x. So this is a to the x ln a. The derivative of a to the x is a to the x ln a. Notice, if you will, that this agrees with the derivative of e to the x if a is e, the derivative of e to the x is apparently e to the x ln e, but ln of e is just 1, so it's e to the x. Why did the e go away doing the inside? Well, what is the inside? The inside is just x ln a. Right? Again, if you want, you should take a moment. If you don't see it immediately, you should take a moment to decompose it as the composition of two functions. Right? F of x is e to the x, and g of x is x ln a. So the derivative of e to the x is e to the x, and the derivative of g is just ln a. So the derivative of this by the chain rule is f prime of g g prime of x. So that's f prime of x ln a times g prime, which is ln a. And here, everywhere you see an x in f prime, you replace with x ln a. So that is e to the x ln a. And e to the x ln a, we just saw was a to the x. So a to the x ln a. There it is. E to the ln, well, that's because exponentials and logarithms are inverse functions of each other. If f of x is log base b of x, well, I should have, it doesn't matter, but if f of x is b to the x, the inverse is log base b. So when you compose the two functions, f of f inverse, you know to be x. But what is this? This is b to the log base b of x. Let me rewrite this new observation right here. The derivative of a to the x is a to the x ln a. And consider this. We are asking the question, what is the derivative? What is dy dx? And what do we have? Well, we have 5 to the something. So the derivative of 5 to the something, 5 to the something ln a times the derivative of the inside. Five to the something ln 5 times the derivative of the inside. Inside is a square root of x. The derivative of root x, 1 over 2 root x. Everybody with us here? Questions? What's the word for this? It's an exponential function, right? A to the x. Well, again, decompose it as a composition of functions. If you don't see it, then that's what you have to do. Let's decompose this as a composition of two functions. What two functions? This is the composition of, you tell me. Anybody? 5 to the x and square root of x. Absolutely, right? Is everybody comfortable with that? So that this is viewed as f of g of x, where f and g are these two. And now, what is the derivative of 5 to the x? Well, the answer is right here. The derivative of 5 to the x is 5 to the x ln 5. And the derivative of root x is 1 over 2 root x. So the derivative of the composition f prime of g, g prime of x. Here g is root x. G prime is 1 over 2 root x. And everywhere you see an x in f prime, you replace with root x. F prime is right here. So everywhere you see an x, you replace with root x. What do we get? 5 to the root x ln 5 times 1 over 2 root x. Right, Matt is asking the question, if we did the derivative of a to the x using the chain rule, wouldn't you just bring the power down, subtract 1 from the power, and there it is. Let's take a value of a. If a is equal to 2, here you're really looking at 2 to the x, whereas Matt is treating it as x to the 2. The derivative of x squared, you bring the power down and you subtract 1 from the power. Not the other way around. This is an exponential function. Not here you were using the power rule. The power rule is when you've got powers of x. This is not powers of x. This is an exponential function, completely different. I've conveniently raised the question we were going to consider. Let's do it again. F of t is t sine pi t. Right, I mean, it's a classic mistake. I rubbed it off because I don't want anybody to take it down and use it as a rule, but it's a mistake a lot of people make. It's important to understand what that mistake was and never do it again. Powers of x versus an exponential function, these are two very different functions. Right, so x squared versus 2 to the x, very different. Right, I mean, you know their graphs. This has this graph, whereas this one has that graph. And the rate of increase here is much faster than that. All right. You're looking at this, and what's the first thing to realize? Right? When you're looking at f, the first thing to realize is that you have a product. Exactly that. So product rule applies. First and foremost, this function is a product. It's t times sine. So product rule applies. Let's do it. Derivative of the first one, leaving the second one fixed. Plus, leave the first one fixed, differentiate the second one. Well, what is the second one? The second one is a sine. Derivative of sine is cosine times the derivative of the inside. Chain rule, always, right? Times pi. So it's a chain rule inside a product rule. Derivative of the inside, derivative of pi times t, pi is just a constant. There it is. Well, Maxwell, if you see a product in a chain rule problem, do we do the product rule first? There's none of that. There's not one thing that takes precedent. You have to look at your function. And how would you read this? T times sine. Product, so it's a product rule. If it had been this to the 100, then what would you have had? You would have had something to the power of 100. You would have differentiated the 100, blah, 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 to the 99, and then you differentiate the inside. So it would have been a chain rule, and inside the chain rule you would have had a product. So product rule inside a chain rule, and then another chain rule inside that product. All right, let's move on. Right, so all I'm saying is, it's not like product rule takes precedent over the chain rule in general. You have to adapt to the problem you're looking at. What are we looking at here? How would you describe your function? You have 2 to the something. The derivative of 2 to the x is 2 to the x ln 2. So 2 to the something ln 2 times the derivative of the inside. Inside is an x cubed. The derivative of x cubed is 3x squared. So why does the t go away? You're differentiating the inside. Derivative of pi t is pi. Think of the pi as 3. Derivative of 3t, 3. Integration is tougher, absolutely, but very rewarding. consider this. Same question as always, we're looking for the derivative. What do you have here? How would you describe this function to a friend? What's the first word that comes out of your mouth if you're describing this to a friend over the phone? Square root. Jacob has put his finger on it. It's a square root of something. Square root of this. We differentiate the square root. Derivative of square root, 1/2, blah, 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 to the negative 1/2, and then you differentiate the inside. What is inside? How would you describe the inside to a friend? The inside is a quotient. So now quotient rule applies. So differentiate the inside, VU prime, derivative of the inside, derivative of the numerator is cos, minus U, V prime, the derivative of the denominator is negative sine, all over V squared. So let's try to simplify that. I mean, we could leave it as that for now, but I suspect it simplifies a bit. So let's do it. Since you have a negative exponent, it means 1 over. We can flip this. This is 1 plus cos over 1 plus sine to the 1/2. Let's distribute this. Cosine plus cosine squared. We knew it was coming. Back. Excellent. Thank you. So sine squared plus cosine squared is 1. So that is 1 plus sine plus cosine. You could cross these out if you wanted to. Why don't we? Why don't we? And what do we get? 1 plus sine t plus cos t over 2 square root 1 plus sine t and 1 plus cos t to the 3 over 2. There it is. Well, it was that time. We knew it was coming. You tell me, what did I do? I just added sine squared plus cosine squared to get 1. Sine squared plus cosine squared is 1, so that's all that happened. if you split this up into square root of the top, square root of the bottom, right? Because you can, if you distribute the 1/2, then you have 1 plus cos t to the 1/2 over 1 plus cos t squared. So all I did was subtract the powers to get a 3/2. Consider this. E to the x over x minus 1. Here you have 1 plus cos t to the 1/2, 1 plus cos t squared. So you subtract the 2 to get 3/2. X over x minus 1. There it is. Differentiate. I think you can simplify that further. Maybe. How so? If you group the 1 plus cosine and cancel it with the 1 plus cosine here, so this and that to give you a 1/2 like this, you know you cannot do that, right? You can only cancel that when there's multiplication. Well, first and foremost, what do we have here? Right? I mean, I read it to you a moment ago, e to the blah, blah, blah. So you differentiate the e first. The derivative of e to the something is e to the something times the derivative of the inside. How are we doing? Derivative of the inside is -1 over x minus 1 squared. Is that right? Exactly. Quotient rule? Absolutely. Right? I mean, e to the something, and this something is a quotient. So quotient rule applies. Now, how was I able to do the quotient rule in my head? It's a good question. Right? Well, now that you know the chain rule, you can use that to your advantage. Practice, certainly, but let me show you a nice trick. Because you know the quotient rule is a bit of a pain. Right? So you can do this without using the quotient rule. We're looking for the derivative of this. Normally you do the quotient rule, but we're going to be smart. And we're going to use a trick. We're going to rewrite this using a nice trick. A trick we've seen before. We're going to add a 0. You're adding 0, you're not doing anything. Right? -1 plus 1. And now you can split it up as x minus 1 over x minus 1. But this is just 1. And this you're going to treat as x minus 1 to the -1. So instead of differentiating this, which you would need to do the quotient rule for, you can differentiate this. The derivative of 1 is 0, so you can forget that. And all you really have to do is differentiate this, which you can do using the chain rule. The derivative of this, -1, x minus 1 to the -2 times the derivative of the inside. So -1 over x minus 1 squared. You can do all of this in your head just by looking at it with maybe a bit of practice. But there it is. And this gives you the power of the chain rule, right? Instead of doing a quotient rule, you could actually do a chain rule. Not convinced? Well, as you know, bald is beautiful. So these are from page, I want to say 206. 206. Yeah. Well, this was the end. We have the derivative, that's all we were looking for. Right? So if we're looking at 38 as somebody suggested, I don't know who it was now. It's a product. E to the negative x times cosine of x squared. So it's a product. Product rule applies. Differentiate the first one, leaving the second one fixed. What is the first one? The first one is e to the something. The derivative of e to the something is e to the something times the derivative of the inside. Derivative of negative x is -1, leaving the second one fixed. Plus, leave the first one fixed, differentiate the second one. What's the second one? Second one is a cos. Derivative of cos is negative sine times the derivative of the inside. Derivative of 2x, derivative of x squared is 2x. There it is. I'll leave it like this to illustrate the whole thought process behind it, right? And you see the product rule and the chain rule in action. There it is. Buffering again? Really? Well, let's hope it doesn't last too long. Where did the -1 come after the e to the negative x? We were differentiating e to the negative x, right? So the derivative of e to the something is e to the something times the derivative of the inside, times the derivative of that something. Deepak, have you tried reloading? Is everything working out there? What about that positive sign? Where is that from? This plus here, plus from the product rule, right? It's this function times this function. So we're applying the product rule. Consider this. What is dy dx? Michael, where have I lost you? Confused about what, right? First of all, it's important that you understand that what we have here, first and foremost, this function is a product. It's e to the minus x times cosine of x squared. So product rule applies, first and foremost. Why is it minus 1, not 1? Because that corresponds to the derivative of the inside. The derivative of negative x is negative 1. Consider this. Let's differentiate. What are we looking at? What is this? This is e to the something. The derivative of e to the something is e to that something times the derivative of the inside. What's inside? Inside is a sine of something. Derivative of sine is cosine times the derivative of the inside. It was sine of 2x. The derivative of 2x is 2. Here, what are we looking at? Sine of something. The derivative of sine is cosine. Times the derivative of that something, the derivative of the inside. What's inside? Inside is e to the something. The derivative of e to the something is e to the something times the derivative of the inside. Inside is 2x. The derivative of 2x is once again 2. Exactly as Shamir is suggesting, if you have 3 functions composed together, which is really what we have here, right? E to the x with sine x and 2x. It's one after the other after the other. Consider this. We're looking for the derivative. When does a derivative have ln in it? Well, I mean, we saw this exponential, the derivative of an exponential. It does look painful at first glance, and it is quite a few square roots, but let's take it one step at a time. How would you describe this to a friend? It's the square root of something. So the derivative of the square root, 1 over 2, that's square root. And now we're going to differentiate the inside. Chain rule, right? So one step at a time. But what if your friend is in this class and you're talking on the phone and you're telling him, did you do 46? And he says, I don't have the book. What is 46? So you tell him it's a square root of x plus square root. So, I mean, now we're going to differentiate the inside. And the derivative of the inside, derivative of x, is just 1. And then, so plus the derivative of this, and what is that? That's, again, a square root. So we're going to differentiate this square root, 1 over 2 square root of x plus root x. And now you differentiate the inside. What's inside? X, whose derivative is 1, plus root x, whose derivative is 1 over 2 root x. There it is. Why did one of the square roots go away after the first step? It did, right? This is to the 1/2, so you get 1/2, blah, 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 to the negative 1/2. So it actually went underneath. Let's do one more. 2 to the 3 to the 4 to the x. This doesn't simplify very much, I don't think. I'd be satisfied with that as the answer. Indeed, these are all ascending, right? Let's differentiate. What do we have? We have 2 to the something. The derivative of 2 to the something is 2 to the something log 2 times the derivative of the inside. What's inside? It's 3 to the something. The derivative of 3 to the something is 3 to the something log 3 times the derivative of the inside. But what's inside? It's 4 to the something. The derivative of 4 to the something is 4 to the something log 4 times the derivative of the inside. Inside is x, derivative of x is 1. There it is. Just take it one step at a time. Looks daunting, but it really isn't. You have to ask yourself, what am I dealing with? What is this? 2 to the something. Start there. What is this? Sine of something. And so on and so on. Exactly that, right? It's called the chain rule because you do it repeatedly like a chain. Could you change that to that? You could not. No. No. Convince yourselves. Convince yourselves if you plug 1 in for x, then those two expressions are different. All right. Thank you all for coming. I will see see you next week. You guys have a good weekend. If I'm not mistaken, is Monday Thanksgiving? I hadn't realized that at the beginning of the week, but I think Monday is Thanksgiving and therefore a holiday. So I will then see you on Wednesday. You guys have a good Thanksgiving. Yeah, so no class until Wednesday. I'll see you on Wednesday. I'll post an announcement just to make sure that everybody's on the same page, but yeah, I'll see you guys Wednesday. You guys have a good one. And happy Thanksgiving to all.